Section: Introduction. In this section, we delve into how transformer-based models, which have significantly advanced our capabilities in understanding and generating natural language, face challenges when it comes to length generalization. This means they often struggle to apply what they've learned to longer sequences than those they were trained on. This limitation prompts us to question whether these models truly understand the underlying algorithms of the tasks they perform, or if they're merely memorizing solutions in a way that doesn't scale to more complex problems. Recent studies have consistently shown that transformers have a hard time generalizing over longer sequences, especially in tasks that involve formal language learning and algorithmic reasoning. This issue leads us to wonder if there's something inherent in the design of transformers that limits their ability to generalize over length. In our paper, we specifically focus on examining how well transformers can generalize in the context of adding numbers with multiple digits, treating this task as a kind of synthetic language learning. Despite its simplicity, this task has proven challenging for transformers, highlighting their limitations in generalizing to longer sequences. Previous efforts to improve this aspect have mainly concentrated on refining how the models understand the position of elements in a sequence and optimizing how data is presented to them. Our comprehensive evaluation led us to a combination that significantly enhances length generalization, using fire position encodings with randomized positions, presenting data in reversed format, and incorporating index hints. Remarkably, our model, trained on sequences of up to 40 digits, was able to handle sequences of up to 100 digits, effectively tripling the length it was trained on. To our knowledge, this is the most substantial generalization achievement for text-based transformers in the context of addition. However, we also noticed that this improved generalization is sensitive to factors like how the model is initialized and the order of the training data. Our main contributions are as follows. We show that the choice of position encoding and data format significantly impacts a model's ability to generalize to longer sequences. By selecting these elements carefully, we manage to achieve generalization to sequences 2.5 times longer than those seen during training. Our investigation into various data formatting and augmentation techniques suggests that their success in aiding length generalization largely depends on the type of position encoding used. Despite achieving remarkable generalization, we found that this capability is delicate, heavily influenced by factors such as the randomness in weight initialization and the sequence in which training data is presented. We also explore recent advancements in architectural design aimed at overcoming the challenge of length generalization in arithmetic tasks with transformers. These include innovations in position encoding and attention mechanisms. However, the effectiveness of these modifications is often limited, either because they are too specific to certain tasks or because they don't perform well on longer sequences. While increasing the size of models and datasets is generally seen as a way to improve performance, previous research suggests that this alone might not be enough to handle longer test sequences effectively. With a growing emphasis on data-centric AI, recent studies have also looked into refining data formats to improve how well existing transformer models learn. Regarding position encoding for length generalization, the difficulty transformers face in dealing with longer sequences than those encountered during training is often linked to how they encode position information. We review various approaches to position encoding, focusing on their ability to help models generalize over length. For data formats, the way data is structured plays a crucial role in helping transformers generalize to longer sequences. This involves transforming the data into a format that the model can learn more easily. We provide an overview of different techniques that have been explored in this area. Finally, we discuss our approach to improving length generalization in decimal addition. This task involves identifying the correct digits to add and then performing the addition, including carrying over digits when necessary. The main challenge lies in accurately identifying which digits to add at each step. Our best performing model uses a combination of fire position encodings, randomized positions, data in reversed format, and index hints to significantly improve length generalization. We thoroughly test each of these choices and explore alternative options in our experiments section. Section Summary. In this section, we systematically investigate the transformer's ability to generalize to longer sequences, focusing on the n-digit decimal addition problem. By experimenting with various position encodings and data formats, we develop a successful recipe for enhancing length generalization, achieving extrapolation to sequences 2.5 times longer than those seen during training. Our findings highlight the critical influence of position encoding and data format selection on the transformer's ability to generalize effectively to longer sequences. Section: Experiments. In this section, we discuss our experiments, focusing on randomized positional encoding, PE, and random space augmentation techniques. As we will show, the effectiveness of these methods varies significantly depending on the PE used. Therefore, we've customized the default settings for each PE to optimize performance. Instead of using random spaces, which could be automatically merged by the tokenizer, we introduce a special token to avoid this issue. Given the high variability in results, we've decided to repeat each experiment 5 times, unless stated otherwise, to ensure reliability. More details on our experimental setup can be found in the appendix. We've also explored how well our model can generalize to different lengths, and we've found that this ability is not strongly influenced by either the initial setup of the model's weights or the order in which training data is presented. Despite using the same training data, 10 trials with different weight initializations showed varying performance, although all managed to learn the training tasks well. This variability was evident in both the consistency of performance over time and across different data orders, even when the initial weights were kept the same. Interestingly, some weight setups seem to be more resilient to changes in data order, hinting at the possibility of finding an optimal, lucky weight ticket that could perform well across various conditions. This observation aligns with the lottery ticket hypothesis, which suggests that within a larger network, there might exist a smaller, equally effective network. Our findings also highlight that, despite similar accuracy on tasks within the training distribution, the model's performance on out-of-distribution tasks varied greatly, underscoring the impact of weight initialization and data order rather than positional encoding. We then investigated whether applying stronger regularization techniques, such as weight decay and dropout, could reduce this performance variance. Our results indicate that while higher levels of weight decay slightly improve the model's ability to generalize to different lengths, extreme values still allow for decent performance. On the other hand, increasing the dropout rate too much can harm the model's generalization capabilities. Thus, while regularization can help to some extent, it doesn't fully address the variability caused by weight initialization and data order. Related work in the field has shown that length generalization is a significant challenge for neural networks, including those based on the transformer architecture. Efforts to improve generalization have mainly focused on refining positional encoding and optimizing data formats. Various heuristic-based formatting methods have been proposed, especially for pre-trained large language models, to aid in arithmetic tasks through in-context learning or fine-tuning. Research on transformers trained from scratch suggests that certain techniques, like reversed formatting and the use of scratch pads, can greatly enhance length generalization. The choice of data distribution and sampling strategies also plays a crucial role in generalization. Some studies have shown the benefits of incorporating simpler auxiliary tasks to support the main task, while others have found that certain types of training set preparation can enable length generalization in encoder-only transformer models. Contrary to these findings, our results with a straightforward random sampling approach suggest that complex data sampling strategies might not be necessary for achieving good length generalization performance.